share the presentations in PDF form and the recording on our home site. And all of you that has been are here today will receive a link to it, so you can also share that with your colleagues and on your websites if needed and wanted. Welcome all of you today. We are quite a few attending this webinar today, so I ask you all to mute and to turn off your camera, please. And we will use the chat quite frequently. So if you have questions, which I truly hope you do have, use the chat, and we have a panel of expertise answering them on the go, but also at the end of this webinar, we have a Q&A session. We will take, though, a couple of minutes after each presentation to kind of go through immediate questions if you have any. So that would be nice if you ask them. Without much ado, I will actually go straight to the program and ask CEO of ITS Norway, Trond Hovland, to wish us all welcome and set the scene for today. Trond, please, the floor is yours if you want to share your presentation.
Am I sharing now, no?
No, you're not sharing it yet. But brilliant, no. We can see that and hear you well. Thank you.
Thank you so much, Jenny, for that kind introduction. And I am Trond Hovland. I'm the CEO of ITS Norway. On behalf of myself and Torunn Degnes, who is a CEO in SAMS, Norway, we are establishing this series of webinars about CITS. So this is a short introduction to today's event, and hopefully you will enjoy that very much. As a carrying idea of most of the ITS around the world, smarter, safer and sustainable transport is like the slogan for what we are doing. We want to create this, and we want to create this in agreement between the users of transport, the society, and also the industry. We need all of those three entities to be winners to be able to actually achieve smarter, safer and more sustainable transport for the future. So we have teamed up with SAMS Norway and ITS Norway, where I come from. ITS Norway is an association, ITS association. It's quite old, 16 years this year. SAMS is a cluster for industry development in the autonomous and mobility area. They are like a young cluster. Both of us have a lot of different goals, of course, but SAMS is very much focused on the industrialization of the autonomous kind of industry business. ITS Norway has had a lot of changing goals over the years, but in this area where we are now, we are also going for industrialization. So at this point in time, we are lining up neatly between each other, and we have the common goals of industrialization. And that's why we also kind of have moved into standards for a kind of a large part. Industrialization demands standards, and SAMS and ITS Norway are deeply involved in standardization. We are both funding standards activities, and we are experts in standards at the same time. We work within the ITS, GIS, building information models. We work within the ICT. We are moving into hubs and into drones to see how standards can help intensify the development of those new domains. But most of all, maybe our task is to bridge different domains. So at the moment, we are working with the GIS and ITS to bridge that gap. And also we are working with GIS and building information models to bridge that gap. So building on what exists and bridge it is something that we do for a living in these two entities. But in general, if you don't have an industrialization of whatever you're doing, if you can't make a profitable kind of outcome of what you're doing, you won't succeed with make the transportation sector smarter and also you can have less emission. So the rationale behind what we're doing is we need open markets to be able to industrialize. And open markets require standardized products and services. Standardized products and services require a lot of formal standardization processes. And formal processes require rules, volunteers, cooperations between all actors and all trades. Thus, there are a need for strategists, experts, funder, and sometimes also regulators into the question. And for this line of work that we're doing here, regulation is a key word. CITS, which we are going to talk to about in this series of seminars. We have this because CITS is actually extremely complex. There are actors from all over the place. We need to understand bleeding new technologies like AI, like machine learning, like telecom, like a lot of things that are on the edge of what we're doing, but still we need to learn them. We need to learn what kind of standardization bodies are out there and how we can work with them. And we need to understand the waste market opportunity and the revenue opportunities that actually exist in the end for us. CITS is basically here to save life, enhance comfort and efficiency, and to reduce emission. That's why we need to fully understand and why we have all these ideas with us. Today we are going to hear a little bit about the technologies and standards involved, what kind of services we can expect, access technologies like the 5.9 gigahertz, sorry for that, security and cybersecurity, data management and ITS station. And all of these things and more that will come in later seminars are actually building up what we call the layers of the digital infrastructure of the roads. So if you have the road surface at the bottom of this slide, you can see that we need the digital driving instructions and description of the physical infrastructure, where we get from the mapping authorities and the road authorities. And then you move up in the stack and you have traffic surveillance and management, you have dynamic traffic information, and on top of that you have actually the user beneficial areas where you have the transportation and mobility, transportation of goods and mobility of persons. And all of these layers need to be understood and standardized and fully kind of penetrable for the technologies. And what is quite beautiful is that in CITS, moving into CCAM, we are actually covering more of these parts of the stack in an easy way and in one go. That's why CITS is so important to understand fully. So this is the daily work for ITS Association, is to actually build this digital infrastructure for roads. But we also are dealing with rail, sea and air transport. So this is only one little part of the whole picture. And then we have the hubs in between. Actors, domains, content, communication, all the families of standards. If you look at the right side of this picture, you have the street sensors with their kind of management and standards. You have the CITS communication between the cars, and you have all the authority on the left side that all needs to convey some kind of information to and from the cars that actually are driving on the road. And there is a void in the middle of this slide, and it's filled with other actors and yet other managements, data management and also actors. So there are so many things to fix before we can have this CITS up and running. We need all this to be able to prevail in the future. But we are certainly underway. This is a little snapshot from the hype curve from the Gardner Group. On the left side, you can see the 2018 autonomous driving level 4 is one of the red circles. And on the next little box from 2019, you can see that both level 4 and level 5 have moved across this hype curve. It's nearing the bottom for level 4. And today in 2020, we are at the bottom when it comes to autonomous real-time data analysis. And also, if you see at the artificial intelligence, cognitive computing, autonomous vehicles is on the bottom of the stack there. So we are moving in the right direction, but we need all these standards to be in place to be able to exploit this thing. And that's exactly what we're going to do with these webinars. I don't know, Björn, if it's called if this is number 0 of 3 or it's 1 of 4, but I dare to call it number 1 of 4 today, January 12th. Key enabling technologies for CITS. Next one is 17th of February, executive summary for the ITS issues. Number 3 out of 4 on 17th of March. CITS place in the CCAM. And number 4 on the 14th of April, business models for CITS. So this makes up the series of webinars that we are entering in today. So I hope that we can enjoy this webinar, and hopefully you will also join up for the next one. Let's engage and learn from the best. And then back to you, Jenny.
Excellent. Thank you very much, Trond. That was very good, and also it's very important for you to note those dates. We will obviously share those with you at a later stage as well, but we would like to continue this because standardization is not just explained in one go, and we need to do that to a broader audience, and that's why we've also started these series of webinars. Very good. Thank you very much, Trond. I would like to introduce you to Knut. Knut, you have already you're already up and running with your video, and now you have your full presentation mode as well. Almost.
I think that it slowly should be getting
yes.
Online. Yeah.
Excellent. Okay. Welcome. Thank you.
Thank you, Jenny. Okay. So today I'll be presenting on behalf of the Norwegian Public Roads Administration, where I'm spending half my time dealing with standards and ITS policy related issues. So why is NPRA as a public body interested in standards? Well, from a European and global perspective, it's because Norway, or in fact the entire Nordic region, have some very specific challenges, in particular in winter, where we have regulations and we have operations that are rather special. But also during summertime, we do have challenges on our road network, and they cannot be solved only on a national level. They have to be international because of the cross traffic and all the goods transport that come over our borders or are leaving our borders. So this has to be international. Another thing is that Norway already have a rather robust digital system in the background. For better or worse, NPRA have been involved in this for quite a long time already. So we do believe that we are quite advanced regarding, for instance, DATEX node for national access point requirements. We do have a road data bank that is rather well filled with information, and it's being maintained. And we also are happy to have a quite good set of services. There are several commercial or semi-commercial service suppliers that do use this information and that supply information, and it's seeing quite strong usage all over. So therefore, we absolutely need standards, and digitalization is not a fly that is just passing. This is a continuous process. So we are deeply involved in management for electronic regulations and national access point, of course, but we are also there to support cooperative ITS in general. So I'm personally rather involved in standardization, as many of you will know. Been in there for, 30 years now. and leading some of these activities. So therefore, I thought I'd bring you through what's happening just now. So we have a number of active working groups. Here you can see a set of them. Electronic fee collection, which has regulatory input to EATS directive. We have public transport that have done a data model called the trans model with lots of underlying stuff that is quite heavily used in Norway. We have working group 4 with traffic and traveler information with the TPEG broadcast information sets. We have working group 7 dealing with the T and ITS, which often wrongly is seen as just an input to the map makers, but it's more than that. But okay, you get the idea. Then we have one of the bigger ones, DataX2 standardization group in working group 8. So these were actually started at the very start 30 years ago and have continuously been maintaining. More newcomers, e-safety for the e-call side. And then we have the big theme of today that I marked red here, which is dealing with cooperative ITS in all its aspects, ranging from physical interface to networking operations to security and all the way up to the different services. After that, we saw a big problem in standards, and that is we are covering quite a few sectors, but nobody are trying to cover the gaps in between. So it's hard to know where to go to fix this. So therefore, we first started something we called urban ITS. But this is not only an urban problem. In particular, in Norway, we see this as a general mobility challenge. So therefore, we introduced mobility integration as a new working group, and I have the pleasure of leading that one. And what we are doing there is to add cross-cutting integration, meaning that we are working together with quite a few of the other working groups. Also, very much working group 16, where we probably have the most close relation and close cross-working situation. This is not only European. Actually, it started out as European, but by now, then the international domain, ISO standards, is even bigger. You can see there are more active working groups. I won't go through all of them. There is a good number of them, but the more relevant for now is to see that some of the ones we had in Europe that I talked about in Europe are exactly the same. And in fact, when you cross-match these two sets, you will see that the European working groups and the international ones are working quite well together. Those who are orange, both on the ISO and CEN side, are working as one joint working group. And that also holds true for mobility integration. So our responsibility is actually to coordinate ITS so that the upcoming standards are as close as possible the same on the European domain and on the international domain. But for the rest of this session, please also note that cooperative ITS or CITS is exactly the same in both CEN and ISO. There are only some minor issues in difference due to voting and regulation process. Core technology, all the stuff behind the scenes, we have managed to harmonize in a good way. Just a few words more about our working group on mobility integration. We have, in our short life, it's only been there for 2.5 to 3 years active. We've had what we call 11 project teams, meaning paid teams, small teams of experts that have written a number of documents. There are about 15 deliverables available today, dealing into all kinds of areas. And for instance, we have taken on to write some new DATEX2 publications, meaning we have produced standards for the DATEX group as part of this harmonization model, so that we are binding together DATEX with other areas. So DATEX is extending its reach, sort of. But also other things like Trond mentioned, mapping and location referencing is a big problem for all the practitioners. So we have made some guidelines how to help them. Yeah, urban vehicle access restrictions is a big thing, and we have made 2 technical standards to help on that, quite a lot actually. But we're not stopping. We are actually increasing our speed if possible. And we have, for instance, seen that a how-to guide is required for finding. There are so many standards and so difficult to find out which standard to use and how it hangs together with all the other stuff. So therefore, we are writing a how-to guide at this moment. We are looking into new areas like curbside and sidewalk management and standardization of that. Automated driving is very much on our table, and we are also doing quite basic work on call it philosophies and architectures for mobility as a service versus mobility on demand. So quite wide spectrum. The biggest thing we are dealing with now, which comes back to the lower part of what Trond showed just now for road authority responsibility, is electronic traffic regulation and how to manage this. It's an essential part, but it's not an, how should I say, it's not an industrial imperative. So therefore, we from the authority side have to cover that. The other part here is on the technology side. And here I would like to draw the lines back to CVIS project, which went from 2004 to 2009. It's by far the biggest ITS project Europe has ever seen. From a research perspective, it's probably the biggest globally. It was, in the end, 43 million. We got 2 million in the end there. And we had 67, 68 partners from 12 European countries. So it was huge. I had the somewhat doubtful pleasure of being the technical architect, sort of the technical coordinator of this. But for the purpose of this presentation, then the green rectangle there is a bit important, because that laid out all the function blocks, all the functionalities that we foresee would be needed in our domain. And then we made a technical reference design that you can see on the right-hand side. Big PCs, 2 of them, lots of antennas, cables, etc. It was a bit messy. Still, functionally, that system behaved exactly the same way as CITS equipment does today. After that, there are lots of different commercial products that have come. And perhaps the most promising one is the green-yellow car you see. That's a Golf 8, which has an included ITS station. Actually, technically, we see the entire car as a vehicle ITS station. So we have come quite a bit from then. My last slide. How will this reference all the standards? The blue, bright blue boxes you see here are the standards we had up until recently. They were sufficient to do the safety type of cooperative ITS, but it could not do the full cooperative ITS over cellular and including back office system and end-to-end security and all of that. So therefore, what you will be hearing more about today are the yellow boxes, because the yellow boxes supplies the missing pieces of the puzzle. How to do the last connectivity, how to do the last part of security, how to do the data models and manage them in a good way. To summarize, cooperative ITS absolutely fully based on standards. It's one of the first areas where I know this to be true. The CYS projects, together with CEN, set the ground rules. We made the first set of standards. And now PT 1605, under the lead of Dr. Fisher, have completed the job and really enable the full CITS promise. So that's more or less it. Did we say we are having immediate questions, Jenny?
Yes, we did. If any of you have immediate questions, if you don't want to chat, you're very much welcome to ask them live as well. So please just put on your camera and obviously microphone and state your name and ask the question. And I think Knut is very available right now to answer any question regarding his presentation. Anything else maybe as well. Anyone has a question, would like to ask that immediately to Knut? Excellent. You have the chance to use the chat function. And if you remember some questions you would like to ask, that's not, there's no, it's not too late. Well, I see already that Thierry has added his presentation. So without much ado, I will wish you welcome, Thierry. And please, the floor is yours.
Thank you, Jenny. Thank you, ITS Norway, for this nice event. So I'm Thierry Ernst, CEO and co-founder of Yogoko. It's a company that is specialized in cooperative ITS.
I think, Thierry, something happened with your...
Yeah, it took time, sorry. I think you see the first screen.
Yes, we do. Now we can hear you. You froze there for a minute, but yes, please.
Yeah, I hope my network is fine. It should be fine usually. So, okay, so Yogoko is a startup company created 6 years ago, and we are specialized in software for cooperative ITS. And basically, we are developing solutions based on cooperative ITS standard. And our major, we say, deployment today are the Scoop project in France. We also have solutions deployed for autonomous vehicles, and actually in the ITS Norway, in the Scandinavian cooperative ITS deployment, we also have some solutions deployed for hybrid communication. So this is a very short presentation of what we do, and basically, I'm sorry, I think there is my network is really not good at the time now. Sorry for that. It should be okay all the days, but just now. So what I want to talk about, and it takes time actually. I already pressed my next slide a few seconds ago, and it really takes time to go to the next one. I don't know why. So I want to speak about hybrid communication, and the slide doesn't showing. Could you just
turn off your camera, Thierry? Maybe that would help as well.
Okay.
Excellent. Thank you. Please.
Yeah, my screen is blocked. I'm sorry for that. Let me try to do something here. Okay. Okay. So the type of the typical example I want to highlight is a scenario where you need to inform vehicles about some traffic hazard. Here, this is a typical example where you have black ice on the road, and of course you want to provide this information to the car that are running right now on just close to the location where the issue is coming. But you also want to inform the vehicle that will come further on. So that means minutes or hours, even days, maybe later. So the question is how to inform all the vehicles in the same fashion, so giving them the same level of accuracy and information so that they could avoid the hazard. That is the issue that we want to solve. And this is just one example of the situations. So basically, it is one technology, localized communication, that allow vehicle A that detects the information to provide this information directly to vehicle B and C, and this without any infrastructure network. That means the information could be provided very quickly So for that you need to have very short latency, and of course using networked transmission through the cloud is not the best if you want to avoid latency. So we have solutions for that. That's V2x communication. So V2x is localized communication between the vehicles and the roadside infrastructure. But for that, you need all vehicles to have the same technology, the same radio, the same protocol. Of course, this traffic hazard must also be reported to the other vehicle that will come later. And that's the question, is how we can provide this information. So the first step is to, of course, provide this information locally to vehicle A, B, and C that are very near the event, but at the same time provide this information through the traffic control center so that the traffic control center can relay that to the vehicle further on using some roadside infrastructure equipment, for instance. So the problem is what happens when you don't have a roadside ITS station everywhere on the road. So if you don't have a roadside ITS station nearby the place where the information, the event was detected, you could use a cellular network to transfer this information to the traffic control center. So this is a way to combine the technology. We have a short range localized communication between the vehicle on the site, and then you transfer this information to the traffic control center that further on transfer this information to the roadside ITS station. And then the roadside ITS station can again transfer this data using localized communication to the nearby vehicles. But again, this might not be true, that there might not be a roadside ITS station ahead the traffic hazard. So you may need to use cellular networks otherwise. The question is how to combine those two technologies, so localized communication using ITS G5 or the radio, and network communication using cellular networks in a way that the same services can be provided. So it's a CITS service, and whatever situation, whatever the network you are in, whatever road, country, region, whatever environment of communication you are, you need to get the same services, the same service, maybe with different, I would say, accuracy or different volume of information, but the same information again and the same service. And this is the key issue that we are trying to address with using combination of technology. So basically, the ITS station, and Knut Evensen already mentioned about that, is an architecture that has been developed by numerous European projects. The CVS project is one of them, and the most important one, and also in CEN, ISO, and ETSI. And basically, this ITS station architecture has been designed to support multiple access technology, multiple protocols, and it's a good fit for to support hybrid communication. It has been designed to natively support hybrid communication, actually. And that means we have the possibility to choose between different technology, and we have standards that are designed to support this selection and this choice of technology. So basically, the aim is really to provide the same CITS services everywhere, but we still want to let everyone, so that every country, every stakeholder group, every ecosystem, to make their own deployment choice. So the same services, the same technologies, but different, I would say, selection of this tool of technology that we have. And for that, of course, a standardized solution is needed, because we want to provide interoperability across all Europe, not only Europe, but also nearby countries and nearby regions. And for that, it's very important that all the CITS services are designed in a way that they are agnostic to the access technology and protocol. That means we can change the access technology and protocol, but we don't need to change the service. We can provide the same service using multiple access technology, as I tried to show in my scenario slides. And also because we want to make sure that we can do a smooth transition from one technology to another one, because new technology appear every few years. So we need to be able to address this, I would say, improvement of the technology and apparition of new technologies. So then for that, we need a choice of methods, a choice of protocols and communication profiles in order to make wise selection, but still managing interoperability and future proofness of the technology. So in ISO TC204, CEN TC278, we have developed some specifications that are generically applicable to all regions, to all needs, independently of the underlying access technology and protocol. And here I name a few of those standards. That's the most critical one. I will not read the numbers, but you will have this information. And basically, this is can be seen as a toolkit. This is not a standard that defines how to use, how to transmit traffic hazard. It's not for that. It's designed as a toolkit for all types of services where you need to combine technology or you need to ensure interoperability. You have those functionalities and those, I would say, technologies, from data format, security method, etc., that are necessary to ensure this service can be performed. And I will name just the ISO 24102 series of standard, because this is where we define the framework of the communication management, and this is critical when we want to select multiple protocol and enforce the choice of a specific communication profile. And there's also 17429, which is a framework for data management. We still need to add new pieces, and this standard, actually, which is published, is going to be revised soon in a multi-part document so that we could accommodate for a specific method, for instance, MQTT or other similar protocols that are needed for the transfer of data in a way that we ensure interoperability. As I said, we need to make sure we can use the technology, but we also need to define what are the data formats and what are the protocols that we want to use to convey the information between the vehicle and the roadside and the traffic control center. And this is still a debate for which protocol is the best fit for hybrid communication support across Europe. Different CITS deployment, pilot deployment have made different decisions so far, and we need to unify that through standardization. So basically, this is the list of standards with the title. I also provide some links where you could find more information about proof of concept, standardization mandate, with additional information on the standard, especially the project team 1605, which has defined the most recent standard on security, on data management, and including the guidelines for hybrid communication. This is the first on my list, and if you need to start from any document, if you want to understand this document is a good starting point to illustrate what are hybrid communication and how it could be supported using a CITS standard. So I'm not sure how much time are left, but anyway, this is my last slide. So you may want to ask one or two questions, and will be available for any information anyway.
Excellent, Thierry. That went very well. We got the hang on that network issue of yours, so we heard you and saw your presentation well. Any questions to Thierry? And a very interesting presentation about hybrid communication, so I'm sure you have some. And you can still, as I said before, use the chat for questions, and Thierry will also be available for latest stage if you don't have any questions right now, but remember them later. Thank you, Thierry, for your presentation.
Thank you.
And, yes,
you're welcome.
excellent. Thank you. Next one in line is Ola Martin. You can start sharing your presentation.
Thank you.
Excellent. Thank you very much.
Is it working?
Yes.
Yes, thank you, Jenny, for the introduction, and to ITS Norway and SAMS for organizing the webinar. I'm Ola Martin Lykkja from Q3 in Norway. I'm working with CITS and positioning. Today I would like to talk about the access technologies at the bottom layer of the CITS communication architecture. So the access layer means the access to communication media. Many people, we very often think about this as something going outside the box, but it can also be internal communication inside the ITS station. Let's like internal in a vehicle to other devices inside the same vehicle. The standards that Thierry referred to supports many technologies for communication, like ITS G5 in the 5.9 GHz band. It supports cellular V2x, mobile networks, infrared, satellite, wired Ethernet, fiber optic, etc. Many technologies. But the most commonly used technologies, and what we would like to discuss today, is the three ones that are in bold texts that I will come back to. I'm going to talk about ETSI G5 and cellular V2x in one as one item in some of the slides, because they are both based on the same concept with medium-range communication, reaching, let's say, 500 meters to 1,000 meters. This is a peer-to-peer technology, so no infrastructure is required. It will go from, the messages go from one vehicle to another vehicle directly without going through a server or to or from a roadside unit. So this is localized communication. The standards for this is described in very much details in ETSI and CEN and ISO and IEEE standards. So there is, if you want to implement this, it's there is no open holes or gaps in the standards. It's pretty straightforward to do it. And this is what is deployed with ITS G5. This is what is deployed today in commercial operation with Volkswagen Golf vehicles, for example. The distinct features with this communication, localized communication, is that the communication is local. It reaches only local recipients, and it's related to local events, like the blocked road in the diagram. Furthermore, local authorities can manage local information. There is no central point of failure in the communication system. It scales well, because if there is a traffic jam in one city in Oslo, it has no implications outside the communication area. It's a broadcast communication technology, meaning that if some ITS station would like to disseminate information about an event, it reaches everyone that's able to listen to that event. Because of the decentralized architecture or decentralized implementation, it's very challenging for Google and other data collectors, data aggregators, to sniff and store everything, because they need to sniff all over Europe, kind of. The communication is in unlicensed frequency bands at 5.9 GHz. There is one disadvantage or a negative feature that's kind of obvious. If there is no peers nearby and there is no one to talk to. So if the purple car moves away from the rock slide on the top picture, there is no one. The yellow car can't receive it because there is no purple car there anymore to send. The other much implemented access technology is mobile networks, 2G, 3G, 4G, 5G, etc. We're coming to, I don't know when the G numbering is ending. This basically offers internet connectivity to the ITS stations using TCP/IP and other technologies we know from internet. This is not a broadcast technology, but it's a point-to-point or a server-to-a-peer technology. The mobile network standards has broadcast features in them, but they never became a hit because of various reasons. So to reach all the corners of the road network in all countries, the coverage and bandwidth is provided by the telecom companies. So there is coverage where the telecom companies find it's economically feasible. And if you want the large bandwidth that everybody is talking about in LTE and 5G networks, you need to have very small cell and a lot of infrastructure. Basically, we'll need to have a cell tower every 1 or 2 kilometers. So the physical distance that a cell tower, mobile cell tower covers is more or less similar to what the ITS G5 station can cover. The distribution pattern is completely different because there must be a way defined in software to figure out how a message that is relevant to local users reach the relevant users. Because in ITS G5, the localization of the event is fitting the localization of the distribution of the message. So you can say that Facebook and Twitter and Google and everybody, lots of internet services give me local information. So this can't be hard to do. But if you care about the privacy of this, it's a lot harder, because the business idea of Facebook and Twitter and Google and all of this is to collect local information about you. We cannot mandate a government system that by law that will collect data in this way. So typically, an ITS station or a system wanted to use the mobile networks needs to have a publish-subscribe architecture that says, I'm in Oslo downtown today, please give me relevant traffic information. An obvious difference between the ITS G5 deployment with roadside units is that for road operators, this is kind of infrastructure-less. The infrastructure is free to them because it's paid by the users and financed by the telecom companies. So the financial model of deployment is quite different. I will just the next slide is about the cellular V2x. This is new technology for ITS communication. So it's actually LTE, and it's using a concept called side link. So this side link is a little bit funny word because traditionally uplink has been used about sending data from the mobile phone to the network, and downlink is down from the cell tower to the phone, and side link is now used to communicate sideways from phone to phone. It's a little bit technical, but it is based on something called sensing-based semi-persistent scheduling. So that is that all the ITS stations in one area, 1 kilometer area, they will kind of negotiate how they will use the time slots available to them. So these blue and red and purple boxes represent ITS messages, and this is kind of so the ITS stations, they kind of cooperate to create this talking schedule. For this to work, you need to have a global synchronized time base on a microsecond level. So this means that to have this working, you need to have GNSS coverage to get the time. Because if you slip on the time, you will start talking while others are talking. So this will not work well. You need to hit straight in your schedule box to be able to communicate. So if you compare the ITS G5 and the cellular V2x communication technologies, so there are different origins based on Wi-Fi technology versus based on LTE technology. It's what they call carrier sense, multiple access versus time slot based. And if you go to the last point, so the ITS G5 is like a polite guest at a cocktail party. You talk and then you let other people talk. But with cellular V2x, it's like a formal dinner at a wedding where you have a toastmaster where everybody needs to prearrange the talking time. So this concept of time is a very, very important difference between the access technology of ITS G5 and Cellular V2x. Then the next challenge with, let's say, internet-based communication to the vehicles. So in this diagram, I have kind of tried to illustrate three different distribution architectures. The buildings on the top are the traffic management center, and they would like to send data to vehicles that needs the messages. So this can be modeled in different ways. That you group in the left diagram, there is only one server that covers everything, like the Twitter or Facebook model. In the middle, there is an interchange that aggregates data from everyone, but then has some part of the population of vehicles belongs to different service providers, here illustrated with OEMs, vehicle manufacturers. The right diagram illustrates how this can be done on a more geographically scoped basis, where vehicles that are in one region talks to the traffic management center of this region, and when they move to a different region, they talk to a different traffic management center. So there is lots of variation here. What is open and proprietary communication? How is the proof of origin of events? How does it scale? What is the privacy implications, and how is it financed? Who pays for it all? So this is just three of many different models, but the current standard doesn't specify any specific model. This is to be defined. Privacy issues. We talked about that a little bit already, but with the ITS G5, there is no central server to wiretap. There is no user and account registry. You cannot steal any passwords because there aren't any passwords. With a TCP, IP, or mobile networks-based architecture and distribution, it can be designed with the same principles. But it's very easy to fall in the trap that you would like to do more with the rich data you get. This is the trap that Norwegian health guys fell into when they did the coronavirus tracing app. They wanted to do more. Yeah. You can always say that it's possible to collect data and anonymize travel location data, but this is very, very hard. It's very easy in many cases to map the travel data back to individual people. And NRK, the Norwegian broadcaster, has article series about that. Yeah, one solution to this is to create a kind of tile concept. This has been explored in Nordic in a sub-project of Nordic Way. So this is that describes how a vehicle in one area can subscribe anonymously to messages in that area. So that means that the service provider doesn't get any detailed information about the driving behavior, speed, and where you are. Finally, I would like to talk a little bit about the security issues in the mobile networks model versus the V2x model. With the V2x model, the security and signatures and verification is very, very good detailed and tightly governed by the European Commission JRC with the European ITS security policy. In the internet, you will typically use X509 certificates, but these are completely separate from the EC trust domain. But the standardization is working very, very hard on this, and transport layer security, let's say HTTPS, is updated with new standards to allow to use the CITS certificates on the internet. So this is a very, very important development that brings these two security domains together, trust domains together. There is also a challenge when you would like to jump between combined ITS G5 communication and internet communication, how you can preserve the trust in the message. Because the protocol, transport protocols, doesn't support that you can keep the certificates or signatures across such a gateway. This was just a small introduction to this topic, so feel free to ask any questions. Here's a small summary of what we have already talked about, so I will keep it there. Thank you.
Thank you very much, Ole Martin. Very good. We have some questions in the chat. Some of the questions I will ask later in the Q&A session because it goes to you all. But there's a specific question to you, Ole Martin. If you could jump to slide number 7. Distribution models on slide 7. Are there any testing of the 3 models different efficiency levels? Of the 3 models different efficiency levels, and to measure up resistance competition between the actors?
I cannot answer that. I know that the middle model is used in the Nordic Way project. So this has been developed and deployed in Norway, Denmark, and Sweden.
Okay. All right. Well, I think that's a good start of an answer, and maybe we find out more if anyone else can answer that question a little bit later as well. Thank you very much, Ole Martin. We will now take a very short break. It says in the program to come back after 5 minutes, so we will keep those 5 minutes. So we will be online again 2 minutes past 2. So please be back for the rest of the presentations and some Q&A. Thank you very much. Talk soon.
Brilliant.
Good, and we will soon start again. And we will continue with the program, and I see there are some questions coming up and I'm answering answers already, so we will also read them out loud just to have them on tape and for you to ask follow-up questions if that's the case. Alex, if you're with us, you would like to share your presentation, that would be great.
Okay, I can do that.
Excellent. And then you can present yourself. Excellent. Okay. Thank you very much.
Right. So I'll be presenting on behalf of Scott today, as he's unable to make this webinar. So hopefully be able to deliver this presentation as well as he hopes. So the core topics this presentation we covering over cybersecurity is what it is, use of IEEE 1609.2, signing off messages, secure sessions, and access control. So, in the context of ITS, cybersecurity refers to the mitigation of attacks on systems or elements of that system. So, system elements are primarily the ITS and its communications payload. For these security provisions are somewhat fractal in nature, the same abstractions at any level of modification of the system. Security is not just about certification or just any one particular point. It requires a holistic, multifaceted approach. So some definitions of security, because how you define security depends on its application and the context. So it can be the state of being free from danger or injury, a form of the collection of documents, facts relevant to finance investment, an organisation's responsibilities for security of the institute's property and workers, etc., etc. And so security is distinct from safety because occasionally these two are seen as interchangeable with each other when they're not. And this includes things like health and well-being, physically, mentally, and will often suffers from a person carrying out a particular activity. Our security deals with, especially in what we're talking about today with ITS, is details which lead to safety, which is integrity, checking who people are, or authenticity, checking people allowed to do things, authority, and keeping their communications confidentiality. So, and this And all these things like safety and security and privacy, they are all interconnect and overlap together. Okay. So you have the conventional transport industry messages, which provide security in the sense of safety. These includes what we all come to expect now in cars, like airbags, crumple zones, intrusion prevention, protection of passengers, pedestrians, drivers. And it also includes things like active and passive safety measures, so road handling, holding, and noise vibration controls. And then all the technical things like ABS, CBA, etc. So security solutions are scalable, and this is the first dimension we have to understand when we are implementing them to a system. So it's things like, is it easy to keep a secret with two parties, which is the basic of symmetric key cryptology. How do we keep a secret with more than 3 parties, which is the basis of asymmetric key cryptology, which is basically public key crypto. And the kind of scenarios we have to be aware of, and ones we like, which are most relevant to ITS, are correspondents know but don't trust another, but trust a network. Correspondents don't know one another, which is the CITS model, and communication networks is public, which is the core model for ITS. And so our security capabilities, which are part of our mitigation toolkit, include primary capabilities of the CIA paradigm, confidentiality, integrity, authenticity, and authority. Secondary capabilities such as availability, reliability, and repeatability, which are enabled by technology such as cryptology, crypto, the mathematical means, key management, key association, key revocation, key renewal, and key transfer. There are a few core lessons to learn when it comes to applying cybersecurity measures and principles. And these include Kirchhoff's principle: crypto systems should be secure, even if everything about the system except the key is public knowledge. Shannon's restatement: the enemy knows the system. For example, one ought to design systems under the assumption that the enemy will immediately gain full familiarity with them. This is also why organizations and systems need measures to deal with zero-day vulnerabilities, and the idea of generalization. The fewer and simpler the secrets that one must keep to ensure system security, the easier it is to maintain system security. This is also to do with the idea of the attack surface and of a system. So the more complex and larger it is, the more there's greater risk of vulnerabilities being found and exploited. So one security philosophy is that open is good, open security over closed security. So from Bruce Shiner, every secret creates a potential failure point. Secrecy, in other words, is a prime cause of brittleness and therefore something likely to make a system prone to catastrophic collapse. Conversely, openness provides ductility. And Belovin, you talked about designing your system to assume that your opponents know it in detail. After that, there's nothing wrong with trying to keep it secret. It's another hurdle the enemy has to overcome. So with ITS being a trust-based system, we have to be able to define trust as confidence in the integrity of an entity or reliance on that entity to fulfill specific responsibilities. Trust is highly dynamic and contextual and may be described in assurance levels based on specific measures that identify when and how a relationship or transaction can be relied upon. Trust measures can combine a variety of elements including identity, attribution, attestation, and non-repudiation. Multiple models for trust networks exist for ITS, and the core requirements related to trust in any system is the identification of the root of trust. Each element is protected within a trust relationship. It is necessary to identify both the root of trust and the path from the protected element to the root of trust. So here are some myths or commonly ignored features about trust. Having a secured communication channel with another entity is never sufficient reason to trust that entity, even if the trust underlying security primitives on which that communication channel is based. Trust is not a binary option. There may be varying levels of trust that an entity has for another. One of the axes for trust is time, and the trust relationship between entities may be highly dynamic over time. So the role of standards in ITS security. So standards help provide a framework for deploying trust. For example, Bob trusts the data he gets from Alice because Charles says it's okay. Bob is the receiving entity, Alice is the requesting entity, and Charles is the shared trusted party. And Alice demonstrates trust by signing data where her signature is verified as authentic by Charles. Bob has confidence or trust that Charles will not arbitrarily verify, notarize Alice. So digital signatures and certificates. Public key certificate holds the key associated to a specific private key, has an attestation by a trusted party of the public-private key association. Digital signature encrypts data, usually with a hash with the private key. A digital signature is verified by using the public key to prove the data can only have been encrypted by the matching private key. There's different types of certification. So you've got identity certificates and attribute certificates. There's a couple of certification standards, but they have many applications. So you've got ITU T, X509, and IEEE 16009.2. And this diagram quickly shows how certificate chains in trust networks work. Okay. Right. And certificates in identity. Okay, so attestation by certification authority of the data offered by the holder, explained here. So the ITS standards for this covers a multi-authority trust model enabled already in the EU for CITS, an efficient attribute-based security model using IEEE 16009.2, expandable identity-based security model using X509, and a single operational security model defined in ISO 21177, which builds on other activity in ISO, CEN, IEEE, and at ETSI. And that's the end of the presentation. Thank you.
Excellent. Thank you very much, Alex. I see there in the chat there are some discussions about ITS G5 and V2x. So you can follow that discussion a little bit in the chat. There are some questions still that I will ask at the Q&A that has not been asked, so I haven't forgotten them. So you know that. Thank you, Alex. You can stop sharing your screen. And then it's Gangolf, it's your turn. So if you would like to share your presentation and put it on presentation mode, and we'll continue from there. Thank you very much.
Hello, everybody. My name is Gangolf Feiter, Concepts and Services Consulting. I'm doing quite a bit of consulting in international standardization for ISO, CEN, SAE, JSAE. I'm 30 years with road vehicle standardization, mainly in vehicle networks, diagnostic protocols, etc. And I have 12 years now with intelligent transport systems standardization in ISO. I'm a member of the CEN PT project team 1605 and the editor of the ISO technical specification 21184, Cooperative ITS data management. This presentation is an introduction to this standard. We have follow-up webinars where we go into more detail. What problem does 21184 Global Transport Data Management Framework solve? The purpose of this standard Global Transport Data Management, the GTDM framework, is to provide a two-way data conversion concept between infrastructure applications and sensor and control networks. For example, for roadside units, vehicles, and ITS, diagnostic applications, etc. 21184 specifies differentiated and secure access to data based on certificates, and this is new, with role information, and complies with GDPR, General Data Protection Regulation. It integrates with the communication security mechanism specified in the 21177, which was also developed within the PT 1605. Then 21184 GTDM specifies the data models for the sensor control network protocols. For a vehicle, it's also called the in-vehicle network, for example, and its proprietary data formats, and the abbreviation is SCNDF. It specifies conversion information into the global transport data format, GTDF, based on standardized data types. The major benefit is a one-time data translation to satisfy roadside, vehicle, personal, and central ITS station facility layer data management. So this really makes it much more simple to exchange data between ITS stations if this facility layer capability is implemented. Here we see a roadside unit with a local traffic controller and its sensor control network. Here is the roadside unit. It got different sensors, radar, cameras. It got the traffic lights, which are actuators. It got a sensor control network, which is the Ethernet here, to the traffic controller. And the traffic controller has a sensor control network, which is magnetic wireless car counting sensors. The Roadside unit, which has implemented Roadside ITS station software, communicates via, for example, LTE, 3G, 4G to a central ITS station system. You could also call it the back office server, maybe for road traffic management. The use cases of the Roadside ITS station are: traffic controller calculates collision avoidance based on vehicle ITS stations cooperative awareness message. Traffic controller controls traffic lights and monitors proper functioning. The traffic controller connects a camera, radar, magnetic wireless, car counting sensors, etc. Traffic controller broadcasts signal, phase, and time messages, which describe the signal state of the intersection and how long this state will persist for each approach and lane that is active. Traffic controller broadcasts map data messages to inform drivers about the physical geometry of one or more intersections. The signal request message requests preempt or priority services for selected user groups. The signal status message describes the internal state of a signal controller. Inspection, maintenance, and diagnosis in case of malfunction. So this is kind of a high-level summary of use cases related to a roadside ITS station. For the use cases of a central ITS station, and that's a much smaller list here, more probably due to available space on this slide than anything else. Remote monitoring of roadside furniture, for example, equipment and how many roadside ITS stations are connected and active. Remote diagnosis in case of error information received from a roadside ITS station. For example, the roadside ITS station identified a defect traffic light. Then city traffic management, which is probably the most obvious one. Status information collection of all roadside ITS stations. So such application on a central ITS station would change the signal phase times on a specific roadside ITS station to improve the traffic flow. Let's take a look at the applicable use case groups. And at the bottom, we see on the left, we see a central ITS station unit. And each computer has sensors like CPU temperature, humidity, CPU load, RAM usage, hard disk drive usage, log files, etc. The same is true for a smartphone, which is a personal ITS station unit. On the very right here, so you have also a accelerometer, temperature, gyro, touch, etc., etc. Then on the second, on the left side is a roadside ITS station unit. We've seen those on the previous slide, and then we have the vehicle with a built-in vehicle ITS station unit, and with the antenna here, most likely the ITS G5 antenna for dedicated short-range communication. Here we see the in-vehicle networks in the vehicle connected to the vehicle ITS station unit, which the generic term is the sensor control network. On the top, we see 3 use case groups. The proximity use cases, so basically the close by use cases, and those have their own protocols to talk to the vehicle ITS station unit or the personal ITS station unit, the other station units. The onboard use cases, this is basically what you know if you install an app from the Play Store onto your smartphone, those are covered. This is covered under onboard use cases. For example, for a vehicle, you would install a pay as you drive application in your in-vehicle infotainment system. Most likely, a different protocol is used to communicate or to access data. Remote use cases cover you know, the ITS use cases, as I've shown before, as well as like something like remote diagnostics, or data is sent to a neutral backend server, for example, or the extended vehicle server. In the middle here, we see a common part and functionality for each ITS station unit. It's separated into 2 colors. Green represents global transport data format. So that is data in a format which can be handled by all ITS stations, regardless of use case. The blue part is ITS station unit specific. You can also call it the sensor control network data format, which is actually raw data. For example, for a vehicle, it's the raw data which you find on an in-vehicle network. They also call it the normal communication data. The challenge is if the blue data would be used in the ITS world, then each and every ITS station receiving blue data would need to know the interpretation vehicle and model brand specific of each and every vehicle driving on the roads. The same would be true if you look at roadside stations. Each roadside station manufacturer, you know, develops its own sensor and control network, so the data, the raw data is different between those stations. And that's the main reason why this standard 21184 has been developed to do a bidirectional conversion between SCNDF and GTDF. And how this is done? It's done through configuration information, which is created offline. And the blue separation line, the dashed line here, which shows the blue part, that is product manufacturer specific and controlled information. And they put this into the blue configuration files. And it includes the information how to access data from a specific sensor or actuator and how it is converted into the standardized GTDF format. How to interpret the GTDF data is contained in the green configuration files, and the pink one, which you can see here, is for access control. And here you see the symbols for security. That means each and every application has to have a certificate in order to be able to access data, regardless of what protocol is used by that application. Data management and cooperative ITS. Data is a key enabler in achieving transport mobility objectives. Open, secure data is a competitive advantage in a mobile society. This is something we have to have. Manufacturers have a right to protect their intellectual property and to demand secure access to proprietary sensor and control networks. So these manufacturers of ITS stations own their sensor and control network data. The CEN ISO 21184 standard is designed to support the rights and requirements of all parties in mobility ecosystems. Vehicle manufacturers are the experts in identifying and provisioning data access to the in-vehicle network. Roadside equipment manufacturers are the experts in identifying and provisioning data access to the sensor and control network. Commercial service and application stakeholders are the experts in identifying their domain. That might be traffic management or diagnostics, pay as you drive, all kinds of application requirements. So clear separation between those who are interested in the data but do not want to deal with raw data of sensor control networks. This slide goes a little more deeply into an ITS facilities layer capability. And the reason is, as I've shown before on the slide with the use case groups, an ITS station has to deal with multiple protocols. Also, Thierry Ernst's presentation on hybrid communication nicely explained this. And what we have defined in 21184 is a so-called global transport protocol handler. That's a set of services, which I will show on the next slide, which is very closely tied to access control. And there is only in the GTDM capability one set of services which is in data format, which is handled and supported by access control and the other function blocks in here, which I will explain in future webinars. So what happens is, if a message comes in, the facility service handler identifies in the header of the message whether it's a cooperative ITS message and dispatches it to this message handler, or if it is a unified gateway protocol message, it dispatches this to this message handler. And if there are more protocols, you know, there could be another 10 here, each has a message handler. And these message handlers translate the protocol specific service and data content into the format of the global transport protocol services. And here is a list of services which are supported. And in the previous presentations, we have heard about MQTT protocol. Those protocols support publish, subscribe, but in order to support also diagnostics with diagnostic trouble codes and data parameters and messages, we have introduced publish values and subscribe values. So you subscribe to a specific piece of information, but you can also subscribe to an entire message. And then every time this message is updated, it gets published. And we have also introduced subscribe DTC information. And those who are familiar with the road vehicles diagnostics protocol, ISO 14229 series, Unified Diagnostic Services, you will find out that all the information contained in that standard is also available in this global transport protocol services here. So you can subscribe to DTC information and say, okay, whenever a DTC occurs, I want this being published so I know what's going on in my vehicle. And then you have a whole list of other services. Important is that these services are supported by the access control configuration, the services as well as the data. Okay, here we have kind of an example, so you get an idea. For example, we have a green configuration here for the GNSS system, for an inertial measurement unit system, which includes the gyro with the G sensor, etc. For ITS G5 system, all the messages, what's contained in such messages would be part of a green configuration part, traffic sign system, etc. We use conversion formulas which are standardized in UDS. Then blue configuration files are product specific. They all specify the messages like SPAT, MAP, SRM, BSM, CAM, etc., etc. And then we have so-called access control protocol configuration and access control permission configuration. Both information is contained in access control configuration. And here we have, for example, 3 roles in the certificate, in a certificate. Each certificate has a single role. Role 1 is road traffic monitoring and reporting to CITS station. Role 2 is diagnostics, and role 3 is a software and configuration update. Here we have a list of services. On the left, the GTP services, and then it looks like a simple matrix, which services and data are supported by which role. And this is the IEEE 1609.2 certificate, and this is referenced in the CEN ISO 21177 standard.
1 minute, Gambas.
Yep, that's my last slide here.
Excellent, thank you.
Yeah, 21184 applies the same methodology as specified in Industry IoT 4.0, Open Platform Communications, Unified Architecture. And you can see this here. Here's a controller. Here is the sensor control network, which is the field bus. Here we have a controller for the press and a sensor control network, and here we have a controller which has multiple sensor control networks. And the conclusion is interoperable data exchange requires data format standards. We have fine-grained data access control through the 21177 certificates. 21184 is based on the same principles, as I said on the previous slide, to IoT 4.0. Worldwide and manufacturer-specific data can be created using the same authoring process, can be merged into the same product via configuration files, and can be mapped to a standardized identifier, including data conversion. Applications from different use case groups require support of different protocols and data formats, There is no single protocol to fit all use cases. And last but not least, the data configuration file concept is more flexible and less vulnerable against attacks than software updates. And that's it. Thank you very much. And next time we will jump into more details.
Very good. Thank you so much. As you all know, we are recording this, so all information will be available and sent to you later on. On that note, thank you, Gangolf. I will then give the word to Hans-Joachim. You may please share your presentation, and we will continue with some questions afterwards. I will read them as the recording does not take the chat into the recording, so we will read some of them. Thank you. Hans-Joachim, please.
Thank you. Can you already see my slide?
No.
Then the sharing failed. I have to try to share once again.
Yes.
Can you see it now?
No, we cannot.
Then this is a well-known bug of Microsoft Teams, and probably I will try again, but probably I can no more share my screen in this session.
Yes.
I try now with the other screen I have. Can you now see a screen?
No, I'm sorry, we can't. It worked
okay,
well
then,
when we tested it. I will share it from my side.
That is great, thank you.
And then you just say, please shift slide.
Yeah.
It works from my side as well.
Hope you find the latest edition I did, but it's not a big issue. Okay, jump to the next slide immediately. And first of all, also from my side, welcome to everybody and many thanks to SAMS and ITS Norway for the chance to give presentations in this webinar. Actually, there had been now, together with mine, 3 presentations from PT 1605 and one that was very closely related to 1605. Status report of this project team that started already in April 2019. We have finished standard development. All deliverables are approved. Most of them are already published or are in the process of being published in ISO and CEN. Next slide. Again, the next. Okay, this is not the latest version, but keep it as it is. About ITS stations, I could talk a full day about ITS stations, but I will make it quite short. The term ITS station is very well defined in 21217, but it is used in different meanings. First of all, it means a physical device used in intelligent transport systems in various implementation contexts, such as at the roadside, in a vehicle, in a central station, or in a portable or personal device. And it has to be noted that such a physical device can also be composed of various physical boxes that are interconnected with a network. And by this, one single ITS station could be spread over 30 kilometers of a highway. Well, in a more strict sense, it is a functional architecture specified in ISO 21217, and we have the latest edition in the year 2020. The latest edition contains normative requirements on security and lifecycle management, beside the huge amount of descriptive text that explains about ITS and the station. And for sure, it is also used as an architectural station model used in many standards to explain the topic being specified. In my presentation, I will have a little bit of focus on service announcement and LDM, as indicated here in the facilities layer. Having a look now on the lower part, which is labeled communications. This is, and you could see this on we'll see it on the slides that are distributed. This I call the operating system of an ITS station, providing all the tools and features that are needed to provide a CITS service by execution of an ITS application, which is on top of these block communications. And as it was said several times, the standards are ready and we can start deployment, and deployment already started and is done, for example, in Austria and in the already mentioned Golf 8 from Volkswagen. Next slide, please. Lifecycle management. This is quite a normal issue if you think about smartphones, smart devices, but it is exactly the same here in an ITS station. We need lifecycle management for every ITS station, which actually is done partly locally, partly remotely. And the remote management links an ITS station to its station management center. This idea was created already in the CVIS project that was mentioned by Knut in the early presentation today. Via such an ITS station management center, you can perform update of firmware, software, and data. There is a series of standards, 24102, that provide the functional behavior description of station management, which you can either implement as it is specified there, or you can implement the functionality in a slightly different way as it is demanded by the technological platform you are using to implement your ITS stations. And as it was said before, we will be very happy to go into more details in subsequent webinars. Next slide, please. Okay, now about facilities. Facilities are tools of this operating system that are offered to the applications, but also to other facilities in the same station. Strictly speaking, according to the model, this is the OSI layers 5, 6, and 7, which are called the ITSS facilities layer. But the layered structure, although it has some benefits, is not always the best way to describe an architecture. Important examples of facilities are a service to provide information on the position velocity of the station and the actual time. The LDM, local dynamic map, which is data storage for data that are referenced by a location and time. Then we have the GTDM framework, which was just presented by Gangolf. The message handler, publish subscribe services have been mentioned several times already, and we have the service announcement specified in EN ISO 22418. Next slide. About service provisioning. CITS is about providing CITS services. And if you want to get such a service, if you want to consume one, you need to have knowledge about existence of such a service. And well, there is a priori knowledge. For example, the Cooperative Awareness Service or the Decentralized Environmental Notification Service. These two are examples of services that are provided by at least every vehicle that has an ITS station by means of broadcast data. That means you know if you are in the vicinity of another vehicle, you can expect that you can use this service because you can receive these broadcast messages, and you just need to implement a parser and extract the data and use the data in the various applications via a publish subscribe mechanism, including the local dynamic map. Another way of getting awareness about existence of a service, you know, from your computer to a Google search, you pull for information. And finally, the technical implementation we have in 22418 is the push of information, where typically a roadside unit broadcasts a message called a SAM, service announcement message, that every vehicle that is passing by can receive and can identify which services can be consumed locally to this roadside unit. To this, we link also the local dynamic map, because usage of the local dynamic map creates so-called virtual roadside stations. Next slide. The basis of this service announcement is an ISO standard 16460, which provides the basic specifications that are used in 3 different profile standards so far. There is one made by IEEE in the 1609.3 standard for the US DSRC purposes. We have an ETSI profile, which is very much tailored to ITS G5. And we have the uppermost generic profile in 22418, which supports all features of 16460 and any kind of access technology. The good thing with the three profiles is if the same lower layers are used to send and receive the SAM and other messages that are essential for the service initialization phase, then we have full interoperability between the three profiles. Next slide, please. And now I go a little bit into the details. And those who know EFC based on the European SEN DSRC, they know about the BST-VST exchange. And this is exactly shown here in these graphics. The BST, Beacon Service Table, is the SAM, service announcement message broadcast to every station that is in the vicinity and reporting about services that are available here. And there is an optional acknowledge message called the SRM, service response message, which is a unicast message back to the service announcer. And this is the uppermost generic way to have service announcement initiated. And there are two other options, which I show on the next slide. The simple mode, which is essentially used by the US DSRC systems and by the ETSI system, where you do not have an SRM, you only use the SAM, and then the receiver of a SAM can immediately start the service consumption. And a feature which I will detail a little bit more at the end of my presentation, where there is an additional private service announcement message. That means we have a somehow extended handshake in the initialization phase, which allows to use, for example, privately allocated radio channels. Next slide. Well, an essential approach in this service announcement standard is the usage of extension elements. That is to say, to apply the concept of information object classes and sets, which allows you to define data elements that are identified by a unique identifier. In these tables, you can read element ID. The element ID is transmitted in the message, and the receiver can derive from this number the details of the coding that follows. That is the length of the element and the meaning of the element, syntax and semantics both. And there are various extensions at various levels in the messages, and although this standard is the result of many years of development, still new extensions pop up. And this is exactly why we apply this concept of information object classes, not only here in the service announcement, but in many of our CITS standards. And finally, in order to manage this, we do not need to update standards regularly, but we need to maintain a registry of these data elements that belong to an information object set. Okay, I want to point to two standardized extensions. First of all, in the SAM extensions, in the top, there you can read with the reference number 84, the extended channel info segment. This extends the usability of the original service announcement that was only available for US DSRC and the corresponding ISO and ETSI profiles of IEEE 802.11 towards any kind of communication technology. That means you could now identify details of a communication channel using infrared communications, millimeter waves, or even cellular technologies. The other one is in the service info extensions at the lower end of this slide with the identifier 85, SAM application data. This is a very interesting approach in my idea, because using this element, this extension, would result in a situation that the transmission of the service announcement message with this element is also at the same time providing the CITS service. In simple words, instead of defining a self-standing cooperative awareness message, we could have identified the service CAM by an ITSA ID, and the SAM application data would contain the whole message. That would definitively simplify the whole architecture of CITS service provisioning. Let us now go to the next and the next slide. Jump over the next, because this is just for completeness. I will now look on the detail how to use LDM in combination with service announcement and this newly proposed extension, LDM Announcer Info. In this case, the service announcement could be transmitted, for example, to vehicle by using cellular technologies, any kind of communication technologies, well in advance of the time when the vehicle will reach the location that is provided in the LDM Announcer Info sequence. There is a location and a time indicating the location where a service is available and the time interval where within which the service, the consumption of the service is reasonable. So to say, having received such a SAM with this extension, the respective information about the service would be stored in the LDM. And once the vehicle reaches the location that is given in this element, data element, LDM Announcer Info, the LDM, as a virtual roadside unit, would present the availability of the service, and the service provisioning could be executed. Next slide. Yeah, well, before we go to the next slide, I can see on my latest version a hint. Sorry, I forgot this. The goal we have is that the format of data stored in the LDM is exactly the GTDM format that was presented by Gangolf in his presentation, this public format in difference to the proprietary formats used in the sensor and control networks. And now actually we are at my last slide with the next one. This is a very special issue which needs the involvement of radio regulations also. You may know that we have for Wi-Fi the so-called BRAN band that is from 5.4 up to 5.7 gigahertz with channel spacings exceeding the 10 megahertz. Just for your information, the 10 megahertz is the channel spacing that is used in the 5.9 gigahertz bands for CITS. Having now a service announcement message at the 5.9 gigahertz band indicating a required channel change to the BRAN band, and combining this with the feature to assign private channels to individual stations, which definitively would require a multi-transceiver system at the roadside, you could significantly increase the channel capacity at a given location of a highway. I will not go into more details of this because then we would need another hour to do this. And we can directly go to my last slide, which gives me the chance to present a little bit my work I'm doing. I'm working as an independent consultant in ITS since 25 years. This is the lifetime of my company, and the lifetime of my company will end of this year because I reached the age that I can slow down a little bit and continue just as a freelancer. That means I will still be with you in the next years, but not with my company. And as with this company, I'm in the project team 1605 and have the pleasure to be the project leader in this PT 1605. Well, I take this opportunity also to say many thanks to all the members of the PT 1605 and also to those externals who helped us very much to finalize the standards in the due time. And with this, I finish my presentation. I'm ready for questions. Thank you.
Excellent. Thank you so much. Kim, there will share my screen as well. Thank you so much. Even though we tested the technology beforehand, sometimes Teams doesn't really play with you, but it worked fine. I see now that the time is about to end. We have quite a few questions in the chat. And as the recording does not take those chat into consideration, we have decided to write them down and the answers as well. And we will share those questions and answers with you, all of you, as we share the link to the to this recording and also with the presentations. So on behalf from ITS Norway, I thank you all. I thank you all the presentators and for your great presentations, and all from you that listen in for your questions. And I hope you will join us next time. As Trond presented in the beginning, we have 3 more dates coming up, and I think the next one is 17th of February. So we will see you then, and have a great afternoon. Thank you so much. Bye-bye.
Thank you, Jenny, for excellent hosting of the meeting.
Thank you.